Okay, so welcome back to another video. Here's a little nice trigonometric identity that we want to verify. So we have a positive integer and we want to show that the following: cosine of 1 plus cosine of 2 all the way up to cosine of n divided by sine of 1 plus sine of 2 all the way up to plus sine of n square is equal to 2 divided by 1 minus cosine of n plus 1 minus 1. So you'll notice our inputs inside for cosine inside, they are not in terms of radians, they're just, positive integers of n, 1 all the way up to n. So in order to utilize such, to evaluate such identity, we can actually use some identities. Well, first thing we notice that we can actually express this in terms of a partial sum, as we can see for both the numerator and denominator. From doing that, we have to actually do things one at a time. So we have to, find the value or the close form for the cosine and then the sine identities. And by doing so, we can actually utilize some a nice identity with the geometric series for the partial sums, turning that actually in the form of a complex exponential form, utilizing that, and then the rest is pretty much just simple. Just utilize some basic trigonometric identities, algebra manipulation. So not a lot of no calculus involved. We'll just put it like that, unfortunately. But this one I feel like is an interesting thing that a nice little trigonometric identity. I don't think a lot of people don't really know about that. I think this is a cool one. So with that, why don't we actually just jump right in? So it's worth noting that both of these sums can be expressed in a form of a partial geometric series. We'll actually use that our partial sum from k is equal to 0 all the way up to the index of k is equal to n minus 1 of x to the power k is equal to x to the power n minus 1 divided by x minus 1. Of course, being that x does not equal 1. So with utilizing this, so x does not equal 1. So with this being the case, so now we can actually turn both our numerator and denominator into the partial sums that we have to calculate one at a time. And it's also worth noting that some trigger identities we're going to be using, so I'll actually just put this to the side. We'll use that 1/2 times sine of a plus b and then subtract sine of a minus b is simply just going to equal cosine of a and then times sine of b, which a and b are going to be, your real numbers and expressing that. So another way, and then another term or identity we'll be using, same thing, but instead in terms of cosine. So cosine of a subtract b, then subtract cosine of a plus b is then simply going to equal to sine of a and then multiply by sine of b. So we'll be utilizing these trig identities later eventually once we get to the nitty-gritty. So first thing, let us actually calculate our numerator so we can see that it's everything in terms of cosine. So we'll start off with that. So first, so we have our partial sum, k is equal to 1 of cosine of k. Then we can actually convert this into a form of a complex exponential function for the trig identity. So that means that's going to be equal to e to the power ik, then add this with e to the negative ik, and then divided by 2. Then we can actually follow from some algebra, some simple algebra, and then using the geometric series formula such that this is going to be 1/2, then multiply by e to the power I n plus 1, subtract e to the power I, then divided by e to the power I subtract 1, add this with e to the power negative I times n plus 1 minus e to the negative I, and then divided by e to the negative I subtract 1. Okay, so that, then what we can do here is let's actually fix this up. So I'll actually divide a e to the power I divided by 2, or negative I divided by 2. So that means that will yield us with the following. So I got some room here, so I'll put it over here. So that will lead us with just 1/2 and then multiply with e to the power I, then n plus 1/2, then minus e to the I divided by 2, divided by e to the power I divided by 2, minus e to the power negative I divided by 2. Then we can actually then subtract. So just because we're utilizing, if you were to multiply and divide, you'll get a negative from the new denominator, and then we can actually just factor out that negative outside. So And that will, of course, you're also rearranging some terms here if that's as well from that side. So then this will lead us with e to the power negative I, then times n plus 1/2, then minus e to the negative I divided by 2, divided by e to the I divided by 2 minus e to the negative I divided by 2. We can close that off. And then what we can do here is let's now actually multiply and divide a 1 divided by 2i. And of course, we're actually going to rearrange some terms together. So by doing so, that means I have, I'll actually just cut to the next footage to actually write out the whole thing in full. So we have this following expression over here. And so then, well, that will just yield us with just 1/2. And then if you actually just substitute, and not substitute, but if you actually use the its definition of the complex foreign identity word backwards, we're going to get that this is 1/2, then times sine of n plus 1/2, minus sine of 1/2, and then divided by sine of 1/2. Close that off. Then if we just utilize our terms, so that means that's because we have these identities over here, we're gonna let our formulas over here, A equals n plus 1 divided by 2, and then B, we're gonna let that equal just n divided by 2. So then if we actually just put everything back together, so now we actually have a new simplified formula, which is gonna be written as the following. We have cosine of n plus 1 divided by 2, then multiply by sine of n divided by 2, all this being divided by sine of 1/2. Okay, so that gives us the partial sum of cosine k. So now let's move on to actually doing the partial sum for sine of k over here. All right, so the next thing we're going to be dealing with is we're going to do our sine expansion. So then that's going to be written as k is equal to 1 all the way up to n of sine of k. Then we perform the same expansion just like before similarly. So n k is equal to 1 of e to the power, use its complex exponential definition. So e to the power ik subtract e to the power negative ik, and then divided by 2i. Okay. So now we just follow the similar formula in terms of, simplification. So that means I have that this is 1 divided by 2i, multiply by e to the power I n plus 1, subtract e to the power I, then divide this by e to the power I subtract 1, minus e to the negative I times n plus 1, subtract e to the power negative I, and then this being divided by e to the negative I subtract 1. Okay, close that off. Then same as before, I'm going to multiply and divide e to the negative I squared, both the numerator and denominator. So we're going to get this following. So 1 divided by 2i, and then now this is going to be e to the power I, then n plus 1/2, subtract e to the power I divided by 2, being divided by e to the power I divided by 2, then subtract e to the negative I divided by 2. Then, of course, I have a minus, and then if you actually rearrange the term, we get a negative on the denominator, so then this will be changed to a plus sign. So then this will be e to the negative I, then n plus 1/2, minus e to the negative I divided by 2, this being divided by e to the power I divided by 2, subtract e to the power negative I divided by 2. All right. So now, same thing just like before, we're actually going to multiply and divide a 2i to the same thing. And it's actually going to cancel out some, well, we're also going to rearrange the terms as well. And then that's actually going to change to have the following. So because I'm actually moving the I, and so some of the i's will cancel out to be a negative, and then that'll change that to a positive 2 on the bottom for the numerator portion. So let me actually write this out in full. All right, so after performing those calculations, then in simplification, we get this following over here, and then we can actually revert this back to actually using its sine/cosine definition. So then that will lead us with 1/2 multiply by cosine of 1/2 minus cosine of n plus 1/2, then divided by sine of 1/2. And then now, of course, using those trig identities we just did over there. So to simplify things out, then we have sine of n plus 1 divided by 2, then multiply by sine of n divided by 2, and then all this being divided by sine of 1/2. Okay, So we already did all that. So we both figure out our cosine expansion and sine expansion. So now we can actually just go back to the original problem, just substitute the things in. So then therefore, that means I'm just gonna draw this black arrow over here to continue on the simplification. So that means doing all this, we're gonna have that, that means this is gonna be the expansion of cosine of n plus 1 divided by 2, then sine divided by, sine of n divided by 2 multiplied by, or divided by sine of 1/2. Then we multiply, because it's divide, so that means I'm actually just gonna flip the reciprocal, so that means sine of 1/2, and then divided by sine of n plus 1 divided by 2 multiplied by sine of n divided by 2. And so this whole thing is being squared, remember that. But also, we have, as you'll notice, that we actually have some terms that's gonna cancel each other out. So we have this gone, and then we have the sine of n over 2 gonna be canceled. So we're just left with these two terms over here. Then this will just leave us with cosine square of n plus 1 divided by 2, then divided by sine square, and then divided by n plus 1 divided by 2 in the inside. So continuing forward, we can actually utilize a nice identity for the cosine square and sine squares and say that this is 1/2, then multiplied by 1 plus cosine of n plus 1, then divided by 1/2, then multiplied by 1 subtract cosine of n plus 1. Then the 1/2 will cancel. You can rewrite this to say that this is the same thing as 2 subtract 1 minus cosine of n plus 1. All this being divided by 1 minus cosine of n plus 1. Then you'll see that this is the same thing written as 2 divided by 1 minus cosine of n plus 1, and then subtract 1, which indeed completes the proof / identity that we want to verify over here, just like that, as you see. Everything comes down to partial sums. To reiterate everything, partial sums of cosine k, sine of k, we actually find its nice close identity for these two over here, right here, and then here. Substitute this back to the original, and then we can actually, do some algebra and also some trig identities to actually simplify things together to get the following just like that. So yeah, that's pretty cool if you ask me.